So what can you do about drift? Drift in RH measurement is inevitable, so plan for it. Start off with headroom, better measurement accuracy than you need. If you need a 3% measurement, then one should not start off initially with a 3% measurement uncertainty or accuracy of the instrument because you have no room to drift. It's also important to control what you can. And that means getting the best calibration that you can, ensuring that the entire measurement system, including the electronics, are of the best quality that you can get. And the RH sensor that you have is the best one that's available for that application, because they are not all created equal. And it's important to look at prevention. Keep the sensor and probe body away from salts or other surface contaminants that may alter relative humidity. It's important to keep things as clean as possible. Do not expose the sensor or sensor body to volatile organic compounds or other solvents or cleaners. That can cause permanent damage. And minimize exposure to high temperature and RH. That can cause both hysteresis and other drift. And don't allow saturation or condensation to occur on the probe body or the sensor, particularly at high humidity levels, as that can also cause hysteresis or in some cases non-reversible drift. It's important to look at instrument specifications as well. Ensure that the calibration is over the entire range that the unit will operate. It's important to look at the temperature. RH sensors respond differently over temperatures, so it's important that they get calibrated over the operating temperature range as well as humidity range. And RH sensors are not linear, particularly at the extremes. So if one were to calibrate, say, between 20 and 70%, yet operate at 10 to 80, you could get some surprises at those extremes. And it's important to look for realistic product specifications. If a specification looks too good to be true, it probably is. If a product is specified from 0 to 100% relative humidity at 2% over the whole range, that may be unrealistic, same as with temperature. One should expect differing humidity accuracy values over a wide temperature and humidity range. It's also very important to look at the as-found value that you can expect. Let's say after a year, what can you expect from a particular manufacturer after the product has been in operation for a year and recalibrated? If that information is not readily available, you may wish to contact the manufacturer to get that information. Now let's look at the needs of an RH monitoring system. A question I frequently get asked is, how many monitoring points do I need? Unfortunately, there's no simple answer. It really depends upon what the application requires. How tight a humidity uniformity do you need in a chamber or in a room? And how uniform is the space or chamber to begin with? You may need to map the chamber or room if you need a very tight uniformity. That will give you a good idea of how many monitoring points you may need. And it's also important to note that you should include the measurement uncertainty or accuracy of the monitoring system whenever you are monitoring a space. Now in this case, we'll look at a room, and temperature uniformity will greatly influence the humidity uniformity. If we were to map this room out and find a 2 degrees C variation in temperature, that alone would yield a 6% humidity gradient throughout that room. Now if we add an accuracy value for the measurement system of, let's say, 2%, we're already at 8%. Now additionally, we would get changes that are seasonal, both between summer when we have cooling coming in or in winter when we have heating. Now that means that if we need good measurement, let's say better than 10% in this particular room, we may need to have multiple monitoring points to truly understand what occurs in that room over time. If, on the other hand, we only need a 15 or 20% value, then probably a single point is adequate. But again, it's also important not to measure just the wall or the corners if we're trying to get a true representation of what's going on in the entire room. Now, in the case of a chamber where the conditions may be much tighter, in this case, we have a stability chamber, which will be operating at 40 degrees C and 75% RH. Now, at that value, just a 0.5 degrees C temperature change will induce a 2% humidity gradient. And now if we add any sort of measurement uncertainty from the instrument, we can easily be at 4 to 5% humidity, which is what we're trying to control to in the first place. So in this case, in a stability chamber, mapping it is probably a good idea. In this example, we've shown mapping on 3 shelves, top, middle, and bottom, with 5 monitors on each shelf for a total of 15. That would really give you a good idea of how many monitoring points are required if you've got good uniformity throughout the chamber. Another parameter to keep in mind in a monitoring system is the response time. The monitoring system must respond fast enough for a given application. A high rate of change and a material or process that's very sensitive, if you don't have an appropriately fast monitoring system, you could miss the change and potentially get into trouble because you don't see it. In this example, we have shown on this red line the true environment, the true swings that may be going on in an environment, both temperature and relative humidity. Now, that's fine, but if we have a measuring system that's quite slow and an alarming system that goes with it, it may not see those excursions. Now, some materials and products don't really respond that quickly, and this may be fine. But in some cases, if those excursions are extreme, like getting to very high humidity or very low humidity, depending on the application, we may want to have a better idea, both recording and sometimes even more importantly, is that we get fast alarming to know things that are going on. So again, it depends upon the needs of an application, and it's important that we select a monitoring and alarm system that's appropriate in speed for the application. Alarming can be an early warning of something that's critical, and if an environment has a recovery time, some early warning can be very valuable. By recovery time, I mean a room where if the humidity gets too low, for example, you have to stop production and rehumidify. This can happen in various manufacturing processes. Now in this case, yes, one needs an alarm to occur when you're at or below the critical level, but having an alarm system that provides early warning, maybe a few % above, can give you time to respond before you have that critical event. It's also important to have alarming if a product may be affected somehow, either high humidity, which can damage certain materials, or even low humidity can cause certain material degradation. So again, if you have a material or process that can be affected by varying levels of humidity, it's important to have an alarming system that will both monitor and respond in a timely manner.